All right, good morning. Let's get started here. So is the take home quiz tomorrow night, right? The deadline for that is tomorrow night, right? The take home quiz is tomorrow night, and then they're all assignments tomorrow night, chapter 6. Hopefully, though, you're well into 7 with all. You've been working into 7, I hope. 7, so 7 is tomorrow. Okay. All right, so I think we're in the right spot. Let's finish this off here. So we're going to look at quiz question 5. So if we look at quiz question 5 here. Okay. We're going to look at hydrogen's electron transitioning from energy level 6 to energy level 3. And it says n equals 2. Why is that not n equals 3? Do I have that messed up? Yeah, this should be a 2. Okay, so we're going to have then the change in energy and from energy level 6 to energy level 2. So we can go ahead and we can actually plug in our equation here. If you multiply all of this together, this number right here, and I have to get the green sheets printed yet. This number right here, if we do these 3 constants, is 2.179 times 10 to the minus 18. Oh, that should be negative 1 over n final squared. It's coming back down to energy level 2. So this would be 2 squared minus 1 over 6 squared. So it looks like I have the answer in joules per atom and kilojoules per mole. This should get us in joules per atom here. So I would do this first. So 1 over 4 minus 1 over 36, it equals, and then multiply that out. So we got 30, 32, 33, 36. One of these we have to cover yet today. All right, 30. So 30, what is a possible set of quantum numbers for the unpaired electron in orthodox box diagram below? It's got to be this one, right? This is the unpaired electron. So if we do the quantum numbers for that, we are in energy level 4. Second number, 0 for S, 1 for P, 2 for D, 1 for P, and then the specific orbitals would go -1 and 0, +1, right? So that one's in a 1. And that one really could be spinning either direction. It looks like we've got to spin it at 1/2. That would be the quantum numbers for that. Okay, 30, 32, 33, 36. 32, which of the following atoms has the lowest first ionization energy? All of these are in group 17 going down. And what happens to ionization energy as you go down the group? As you go down the group, ionization energy decreases going down the group. So it looks like the lowest first ionization energy should be at the bottom of that radio. 33 we're going to cover today. 36. Did I miss one? 36. All right, 36. write this out. So we've got nitroglycerin. Oh, I balanced. We're going to balance this pig then, huh? We're going to get to balance this. So we don't have the nitrate. So if I tried nitrogen here first, we're going to start with carbon or nitrogen. We've got 3 carbons here. There's 3 nitrogens here and 2 here. So let's go. We're going to have to make that 6. So I'm going to have to go 2. Make that a 6. Make this a 3, huh? That gives me 10 hydrogens. So I'm going to put 5 there to do 10 hydrogens. Oh, do we have 18 oxygens? 12 and 5 is 17. We've got 19. What do I got going here? 12, 17. I've got 19 oxygen on the right. I've got 18. What's up here? What do I mess up on this balance? Or do I have it? 6, 10 there, 3, 2, that's 6, 12 and 5 is 17, that's 19. I've got 18 there. Where's my balancing mess up? Who's got this balanced? Who has this balanced? Or is it impossible? It's impossible? Nobody has this balance? Not a single person in here has this balance. What do you got? There should be a 4 here. That's 4. Yep, so double everything. 6, 10, and that gets us a what? 2 here? No, that's it, huh? That gives us 36. So 24, 34, 36. That's right. Yep. 4, 12, 6, 10. What mass of nitrogen gas is produced? 0.3 moles. So there's 0.3 moles here. We have to get nitrogen gas here. My mole ratio fraction is 6/4. So 1.8 there. And then once you get the moles here, we have to get the grams. And then we're going to go 1 mole of nitrogen is around 28.02 grams. Okay, we will talk about 30, I think is the one today to finish up. All right, let's finish up where we left off. Get this in the books here. So we left off, we filled in some periodic trends last time, and we left off right here. So we're going to finish up with a couple of our questions. Okay. Using order periodic table, arrange the following elements in order of increasing atomic radius. Well, atomic radius increases this way, and atomic radius decreases this way on our periodic tables. So what do we got here? We've got all noble gases in group 18, the way it looks, huh? Starting with helium going down. Looks like it's group 18. So it says arrange a volume in order of increasing atomic radius. Well, we can just do that going down then, right? So if we put that in order, we can say helium is less than neon, and neon is less than, we skipped argon, that's krypton, and krypton is less than xenon. In order of increasing, that would be correct. The next one here, order of increasing ionization energy. So we know ionization energy does this. We know going down, it's a decrease. And going across, it's an increase. And it looks like we have everything in group 1, huh? What do we got here? We got hydrogen. We got sodium. We got potassium. And it's skipped rubidium and it's got cesium. Okay, so increasing ionization energy then, if it decreases going down, it's going to increase going up. Right, according to this term, increasing ionization energy is going to be this way. So then we could say cesium is less than potassium, and potassium would be less than sodium, and sodium would be less than hydrogen. We could put it that way. Okay, this atomic radius, this is a quiz question, and so this is our quiz question, same thing. But I've got it on another page here, so let's go look at that. I've got it on an upcoming page right here. So let's look at this. Look back and look. Our question. Ionic radius, yes. Okay. If we look at this page here, all of these, and these are called isolated electronic ions. They have the same number of electrons. The same number of electrons. So first of all, what are these? What is the Lewis of this? If they have the same number of electrons. I just picked one of these out, it wouldn't matter. Let's pick up this fluorine right here. Let's add an electron to it. So for fluorine, This is our number of protons. We can put it right down here if we want. I've got here 7, 8, 9, 10, 11, and 12 protons. So fluorine with 9, it would be 1s2, 2s2, 5, right? That's fluorine with 9 electrons. And I would have to add this 1 electron here for the negative charge, correct? Add 1 electron there. Configuration as what noble gas? This is the same configuration as the noble gas neon, right? All of these are exactly the same. Here, I would have to add 2 electrons. Here, I'd have to add 3 electrons, correct? Here, I would take away the 3s1 electron to get +1 charge. And here, I would take away a 3s2 electron. All of these have the same electron configuration, and that electron configuration is the same as a stable neon. So what happens to the radius of these atoms? Excuse me, ions. These are all ions with a charge. So I added this down here. I took this table out of the textbook, but then I added this. So this is the atomic radius of the neutral atom. So what happens when you make a negative ion? It's more than double, correct? You're adding 3 electrons. You have the same number of protons pulling in 10 electrons. It gets bigger. What happens when you go from oxygen with no charge to oxygen with a -2? It should get bigger. You've got 8 protons pulling in 10 electrons. Which one's the biggest? Well, this one here, because you only have 7 protons pulling in 10 electrons. When you get over here, fluorine, it's 42, and it goes to 133. You had 9 protons pulling in 10 electrons. But now we're going to go the other way. Notice what happens here when you form a positive ion. This gets right. We are getting rid of level 3. Let me take this one right here. You have neutral sodium atom. 1s2, 2s2, 2p6, 3s1. That's the neutral sodium atom. What does that have for a radius? 190 picometers. Well, you get rid of that level, correct? What's the radius of the atom? It's about half. Magnesium here, you get rid of 2 electrons. And this is kind of typical. This is about half. This is about half. This is almost triple, right? Going the other way, almost ×3. But there's our exact order of our radius. This is the largest, this is the smallest. It's really how many protons are pulling in the same number of electrons. Obviously, 12 protons should be able to pull in 10 electrons tighter than 7 protons pulling in 10 electrons. So let's go back to that question. If we go back to that question, arrange the order of increasing atomic radius and +2 sodium oxide nitride. So increasing radius, then the smallest, again, followed by sodium, followed by oxide, followed by nitride. How does OWL put this in? They don't have a less than sign here. They just put it in this order in the boxes. Who's done this? Order from left to right. Okay. All right. So again, you just have more protons pulling on the same number of the electron. So here we have the electron configurations of ions. And this slide or this page is not perhaps, I don't know that well done, I guess, but let's look at this. This is a neutral atom right here. This is fluorine, right? Just a neutral atom. 1 is 2, 2 is 2, 2 5. What does it do to become fluoride? It takes on this electron, right? So we get this 6 right here from 5 plus 1, right? And this is the same as the noble gas electron configuration. Remember, they all want S2P6. This is the same as neon, right? Here is an atom of sulfur. What's the charge on an atom? It doesn't have charge. Sulfur gains 2 electrons. 4 plus 2, you've got 6. This is now sulfide. And what noble gas configuration do we have? Sargon, right? How many valence electrons do all these have then? How many valence electrons? 8, right? How many valence electrons? 8. Just like our noble gases. That is the most stable configuration. So those are some negative ions. Positive ions, we're going to give up an electron. Here we're adding electrons. Here we're giving up an electrons. Others just cross them out. You're left with what noble gas configuration here again? For a sodium ion. All right. Okay. Germanium plus 2 ion is, in this case, it got rid of those 2's. Look at once. But that's not what it is. So I'm looking at germanium. Germanium is always plus 4. Always plus 4. It gets rid of those 2 and gets rid of these 2. Brings this to a 4. We have a full argon and a full 3D. Okay, again, just neutral atoms over here. This explains somewhat how we get the charges that we get. What do we got here for iron? Iron is going to get rid of these two right here. There's your iron plus 2. And if iron plus 2 here, here's my argon. My iron plus 2, oh, this is not. Then iron for a plus 3 charge, if it gets rid of 1 electron out of the D, ends up with 3d5. 1, 2, 3, 4, 5. It would look like this. And that is pretty stable. And it stops right there. Iron does not go farther. Iron is a 2 or a 3. No, it does have a 6 on here. That's pretty rare, but this is pretty stable. Okay. Let's finish this off here then. So 2 electrons of helium have different values for the spin. That is, they have opposite spin orientations. So for helium, it only has 2 electrons, right? In helium, it's 1s2. So we simply have to do this, right? 1s2. We know they have opposite spin orientations. We say their spins are paired, and the result is that the magnetic field of 1 electron is canceled out by the magnetic field of the 2nd electron with opposite spins. Elements and compounds that have unpaired electrons are attracted to a magnet. Such species are paramagnetic. All electrons are paired with 2 electrons each having opposite spins, experience a slight repulsion and subject to a magnetic field, so they're diamagnetic. Paired with opposite spins. So if we go to the next page, we just got a couple examples, and I'll does this towards the end. So this comes from our box diagrams for electron configuration notation. So unpaired. So if this right here, this is an unpaired 4s. That's my unpaired 4s1. All of these are paired, 3d10. 3d9, then this one right here is unpaired. So paramagnetic and copper with +2 would be diamagnetic. You're just looking to see if you have it unpaired. The way to remember this is di meaning two, they're all double. Right? Di meaning two, they're all double. Then I think finishes off with this isoelectronic, where again, the number of electrons are the same, but different numbers of protons. The number of electrons here, we say all of these are isoelectronic. All of these have the same number of electrons. So let's see, we got one problem, two problems from our. Considering only ions with charges of +1, +2, -1, and -2, or neutral atoms, give the symbols for those four species that are isoelectronic with potassium. Well, let's write that out first of all. So we have potassium. It has a plus charge. Potassium has 19 electrons. So we're going 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. But this 4s1 is a neutral potassium atom. Oh no, that's my potassium ion. I'm going to get rid of that. So this remaining here is exactly the same electron configuration rotation as what metal gas? That's argon. So all of these are going to have how many electrons? 18 electrons. All are going to have 18 electrons. So this includes argon. The neutral atom is the argon. So your first one's argon. Right here. So we did potassium. Potassium, +1 charge, 18 electrons. It's 19, we get rid of 1 electron. And argon. Get rid of 2 electrons. Where's our +2 charge? +2 charge is going to be calcium, right? If calcium gets rid of 2 electrons, it starts out with 20 electrons as a neutral atom. If it gets rid of 2 electrons, it's going to take on a +2 charge and have how many electrons? 18, right? So our +2 charge is going to be calcium. Then we're over here add an electron to chlorine, we get a -1 charge, and we have the same number of electrons as argon, right? So our -1 charge is chloride. Our -2 charge is the sulfur. Sulfur has 16. If it takes on 2 electrons, it's going to be -2. So we have sulfide. So, yeah, that does it right there. Argon has 18 protons. Calcium has 20 protons. Fluorine has 17 protons. And sulfur has 16. But they all have the same number of electrons. The same 18 electrons as argon. That is the goal, to try to get S2P6, same as a noble gas. Okay, the last question. Looks like this. You have a monoatomic ion, that's a single ion here, with a charge of -1. Its isoelectronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. What is the ion? So this right here is the ion. What is the atom? If that's the ion with a negative charge, then the atom is going to be 1s2, 2s2, 2p6, 3s2. It is the atom, isn't it? This is the -1 ion. Added 1 electron right there. What did it start at? A P5. So what is this? 2, 4, 10, 12, 17. What element 17? Chlorine. And the ion is chloride, right? What is the chemical symbol of a noble gas? This ion is isoelectronic with argon. Formula for the ion, I thought I just did that. Is it like this? Okay, that finishes up chapters 6 and 7 together. So with that, we are going to the last learning guide. And we're going to look at the last learning guide. I'm not going to have you do quiz questions for that. But for the last learning guide, so this is all together. This is chapters 8 and 9. And for your homework for this, you fill a book around in 8 and 9. 9's a beast. Got some examples. It's not easy to figure out how to put them in and what they're asking for. But 8 and 9 will finish us off here. I think we're on schedule. We're not trying to cram anything in at the end. I think we're on a perfect schedule to get done. Okay, so chapter 8 is on chemical bond formation, Lewis electron dot structures. And here's some pretty good videos. But we'll look at some bonding here for covalent and metallic bonding and ionic bonding. So if we talk about ionic bonding first. A good example for ionic bonding is typically you have a metal with a non-metal. You're going to have an ionic bond. Typically metal with a non-metal. What's the best example of that? Metal, non-metal is what we have down below, sodium chloride. If we write out the configuration for sodium, zero charge, we would have 1s2, 2s2, and then 3s1. Here's our one valence electron, right? That's a valence electron. But we know sodium wants to get rid of that one valence electron, correct? For sure, to become more stable, to have the same electron configuration as the noble gas, right? Okay, so here we if we do chlorine, it would be 1s2, 2s2, 2p6, 3s2, and 3p5, right? Neutral chlorine. How many valence electrons? 7, right? This right here actually shows our valence electrons. So we represent these as dots. Here's my one valence electron for sodium. Here is my 7 valence electrons for chlorine. And I'm going to make this one an X. So we know that when we talk ionic bonding, we're talking about the transfer of an electron. So sodium does not want this electron. If we get rid of that electron, who wants it? Chlorine. If sodium gets rid of this one electron, it has the same noble gas configuration then as, that's neon, correct? Same as neon. Chlorine adds one electron. Adds that one electron. X right here. This is the one electron from sodium. then becomes the same as the noble gas configuration of sodium ends up with neon's number of electrons, electron configuration, and then chlorine takes on one electron. It has the same configuration as argon. In the end, how many valence electrons for both? S2P6, 8. How many valence electrons over here? S2P6 or 8, right? So there's our ionic bond. So we think of a electron transfer. Then you can make an ionic compound. Okay. If we do covalent bonding, the word is sharing electrons, not transfer. Covalent bonding is sharing of the electrons. We're going to share those outermost valence electrons. Okay, that's what's talked about in 8.1. And 8.2, covalent bonding in Lewis structures. In molecules or polyatomic ions of only non-metals. Atoms are attracted by covalent bonds. So for this, polyatomic ions, NO3 minus, or -3. Covalent bonded non-metals, think carbon monoxide, carbon dioxide, water. All non-metals. All right, 4 in valence electrons. For group A elements, groups 1, 2, 13 through 18, valence electrons can easily be predicted from the periodic table. Core electrons are not involved in bonding. So if we go to our periodic table, our previous blank periodic table, go to this blank periodic table. How many valence electrons for everything in group 1? 1, correct? 1 valence electron. What charge do they take on? +1. If it loses that valence electron. Everything in group 2, how many valence electrons? 2, right? When we come over here to group 13, how many valence electrons here? This is 3 valence electrons. S2P1 is 3 valence electrons. Group 14, 4 valence electrons. S2P2, group 15, 5 valence electrons. Group 16 is 6 valence electrons. Group 17 is 7, and group 18 is 8, except for here. So we're going to use that all the time going forward. It's the ones place here. Here's valence electrons. We know group 1 has 1 valence electron, group 2 has 2. Over here, it's the ones place. The number of valence electrons in these groups matches the ones place. All right. So we just did this valence electrons. So American chemist Gilbert Newton Lewis introduced a system in which the symbols represents the nucleus and the core electrons, and the valence electrons are represented by dots. So on the next page, it says, draw the atomic symbol. This represents the atomic nucleus along with the core elements for electrons. Now, what are core electrons? Are just not the valence electrons. So here's an example. We have calcium. 20. 1s2, 2s2, 2p6, 3s2, 3p6, 3s2, 3p6, 4s2. So my core electrons here is right here is the core electrons, the non-valence. Same as the noble gas argon. We do it Lewis structures. We write down the symbol. This represents again the core electrons and the protons in the nucleus. Then we have boxes, top, bottom, left, right. Typically, we treat each side as a box that can hold up to 2 electrons. Count the electrons in the valence shell. Start filling boxes. Don't make pairs unless you need to. So if we did this for calcium, and we just start putting in electrons, it doesn't matter, you can just space them out. Here's some examples. This is table 8.1. So lithium and sodium just have 1 valence electron, right? Group 2, beryllium, magnesium, 2 valence electrons. We're putting them left, right, it doesn't matter, just don't match them up. This is group 13. Is going to have 3 valence electrons. Group 14 is going to have 4. So 1 left, right, up, down. Group 15, now we start pairing them up. Group 16, group 17 has 7, and then finally we get to group 18. Again, these are valence electrons, these are the ones for us, right? Okay, we're going to do Lewis structures because I'm not sure the arrangement, the way this goes, and Al kind of does this backward. It's like, well, which of the following is not a correct Lewis structure? Well, you haven't drawn a Lewis structure. Well, it's kind of hard to judge it, first of all. So we are going to go right into drawing Lewis structures. For chords, where is this baby? It's the last one. Towards the end, you see this. Directions for drawing Lewis structures. And then we're going to start on the page after that. So page way towards the end, and you'll see directions for drawing Lewis structures. All right, so let's go to the next page here. And we're also going to use our blue sheet that you got day one, I believe. Everybody have a blue sheet? Do I need to bring any blue sheets next time? One blue sheet, two blue sheets, four blue sheets, five blue sheets. All right, I think I gave them all away. Yeah, I'll have to bring some blue sheets and the modified green sheets. Okay. So we're going to do CH4. Sounds like the microphone this one. I'm going to talk loud. We're going to do CH4. Right? First step is to count your valence electrons. Total valence electrons. And for carbon, we have how many valence electrons for carbon? What group is carbon in? Have one carbon atom and it is in group 14, so it has 4 valence electrons. For hydrogen, we have 4 hydrogen atoms. How many valence electrons for a hydrogen atom? 1. We add this up, we got 4 plus 4. We have 8 valence electrons. All right, I'm going to make sure I am following the instructions. So I'm going to page back. All right, count the number of valence electrons. I did number 2 first. Number 1, write the skeletal structure, the arrangement of atoms within the molecule. The central atom is going to be the lone atom or the atom with the lowest electronegativity, usually written first. C and P are usually central atoms. I've got a typo in here. I'll have to look up. Hydrogen is always a terminal atom around the central atom. O is usually a terminal atom. Okay. So step 2, count the valence electrons. Let's clarify that. It's Add electrons for negatively charged ions and subtract electrons for positively charged ions. So carbon is going to be my central atom. I'm going to put carbon in the middle. I've got 4 hydrogens. Hydrogens are always on the outside. I'm going to put them as far apart as possible. The bonding electrons are going to repel each other. We need to put them as far apart as possible. And on 2-dimensional paper, all I can do is to put them far apart as possible, is to put them 90 degrees apart. In order to bond these, 2 electrons. So we're adding 2 electrons. So I've got 8 electron dots. I'm only allowed 8 electrons. I'm done, and I have a nice Lewis structure if carbon in the middle has 8 valence electrons, or 8 electrons around it now that it is sharing with hydrogen, and it does. Oops. Carbon has 8 electrons. It is sharing 1 electron from each hydrogen. Hydrogen has how many electrons around it? If it shares 1 from each carbon, or from the carbon? 2, correct? Hydrogen has 2 valence electrons, just like the noble gas helium, right? Carbon is going to end up with 8 electrons when it shares, and the hydrogen is going to end up with 2 electrons. This is not going to have any multiple bonds or resonance structures. We'll get to that. Now, I have this term here, bonding domains, non-bonding domains. For our bonding domains, any bond, I messed up, I went off the paper. Any bond counts as 1. Now, what do I mean by that? Any bond counts as 1. I have a carbon single bond. If I have a carbon, I got to put 2 electrons in there, sorry. This would be a double bond. It would look like this. Or a carbon-carbon triple bond. All of these count as 1 bonding domain. It doesn't matter if it's a single, double, or a triple, 1 bonding domain. A non-bonding domain, this is a pair of electrons. Pair of unbonded electrons.
A pair of unbonded electrons. Central atom. So, how many bonding domains do I have here? I've got a single bond, single bond, single bond, single bond, right? This is 4 bonding domains. How many unbonded pair of electrons are around carbon in the middle? How many unbonded pairs? 0. Grab your blue sheet. For those that have a blue sheet, remember, look up bonding domains, non-bonding domains. Find 4, 0. Bonding domains, non-bonding domains. Four, 0. Right? 4, 0. What is my shape? Tetrahedral. What is my bond angle? 109.5. My hybridization, I could put in, that's on there as well. We're going to explain that later on. sp3 hybridization. My electron pair geometry, molecular geometry, and angle. Let's clarify that. My electron pair geometry is possible bonds. My molecular geometry is actual bonds. So in this case, my electron pair geometry is 4, 0, is tetrahedral. All my bonds, all my electrons are bonded. So my electron pair geometry, my molecular geometry match. Both of these are tetrahedral. And my angle is 109.5 degrees. Tetrahedral, tetrahedral, 109.5 degrees. I'm going to show you what that looks like before we get out of here quick. All I got to do is switch over. So here is what that looks like in 3-dimensional space. This is in 3D. We drew it on a 2-dimensional page. It looks like on our 2-dimensional page, they are 90 degrees apart, but they are not. These are all 109.5. This is a 4, 0 for bonding domains. This is water. Water has 2 pairs of electrons. So my bonding domains for water would be 2 here, and my non-bonding domains would be 2. So when you look this up on your blue sheet, this would be a 2-2. 2 bonding domains, 2 non-bonding domains. Carbon dioxide, double bonds count as 1. This is 2 bonding domains, 0 non-bonding. I could have something like this. This has 4 bonds, 4 bonding domains, 2 non-bonding domains. So we will hit this hard next time we meet. We'll do a bunch of Lewis structures.